Okay, welcome everybody. So we are going to continue working with vector spaces and bases. And what our focus is now going to be is how can we change representations coordinates from one basis for a vector space over to a different basis of the same vector space. And so we've done this previously when we talked about change of coordinates from a non-standard basis B into the standard basis in Rn. So just recall that if we take our vector space V to be Rn, so we're not going to be thinking about matrices and polynomials or more abstract vector spaces at first, but we will eventually. And let's say that Rn has some basis b1, b2 up to bn, which is, say, different than the standard basis. Then we define the change of coordinate map, which goes from Rn back into Rn, where we take vector x and we map it to its representation under the b coordinates. And this map we saw can be achieved by applying what's called the change of coordinates matrix, which consists of n columns. Each column in this matrix is one of the basis vectors in our non-standard basis B. And sometimes we may want to go from a standard basis into some non-standard basis B. And so in that case, we just take the inverse of our change in coordinates matrix. We find P inverse, and that's going to be the change of coordinate matrix from the standard basis into B. So let's take a look at an example to refresh ourselves about how these matrices work before we start to think about how we can convert from one set of coordinates to another set of coordinates where neither of the bases are the standard basis. Okay, so let's take a look at a concrete example to refresh ourselves about how we can work with change of coordinates matrices. So here we're going to consider vector space V to be R2, dimension 2 vector space. So let's consider two different bases, neither of which is the standard basis. So basis B consists of two vectors. The first vector is 2, 1, and the second vector is minus 6, 1. And basis C consists of two different vectors. The first vector is 5, 3, and the second vector is 2, minus 2. And because these vectors are linearly independent, and there's two of them, which is equal to the dimension of the vector space, then we know that each of these sets, which consists two linear independent vectors, must span the R2, and therefore these are both bases. So question 1 is saying, let's take this vector, which is written in B coordinates, and let's write this in terms of the standard basis. So just recall what this means. This vector 1, 6 relative to the coordinates, rather to the basis B, means the vector, which is going to be 1 times the first column vector plus 6 times the second column vector in our basis. And we can calculate that by multiplying this vector 1, 6 by the matrix whose first column is 2, 1 and whose second column is minus 6, 1. And here we can check that the matrix multiplication is going to give us a vector which is minus 34, 7. So that means this vector 1, 6 written relative to B coordinates, this is the same thing as taking 1 times this vector plus 6 times the second basis vector. So that results in the vector minus 34, 7, which is in terms of our standard basis. So this is really a vector which is 34 units to the left and 7 units up. The next question is asking us to take the vector 1, 6, which is written in standard with respect to the standard basis. So this is a vector which is 1 unit to the right, 6 units up. And I want to write this in terms of the basis C. So in other words, I want to say how many times would I need to multiply the vector 5, 3, and then add some other multiple of the vector 2, minus 2 in order to wind up with the vector 1, 6. So now we're going from standard basis to non-standard basis C. So the first thing that we could do is set up a change of coordinates matrix that would go from C into the standard basis. And that would have a 2x2 matrix whose first column is 5, 3, which corresponds to the first basis vector in basis C. And the second column would be 2 minus 2, corresponding to the second basis element in our basis C. So this is a map from C to the standard basis, but we want to go from the standard basis into C coordinates. So we can invert this matrix. And in this case, for 2x2 matrices, where I got this inverse from, if you want to verify this work, is recall for 2x2 matrices, we can find the inverse by multiplying by 1 over the determinant. And so in this case, the determinant would be minus 10, minus 6, minus 16. So that's where this leading minus 16 comes from. And then we interchange the diagonal entries. So that's why I have a minus 2 here and a 5 here. And then we change the signs of the two off diagonal entries. So that's why we have a minus 2 here and a minus 3 here. So this entire matrix, including the coefficient out in front of it, this is inverse of PC. So this is how we can go from standard basis to C. So I'm going to take this matrix, which is now the inverse of P, multiply the vector 1, 6 by this matrix, and we wind up at this vector, which is written relative to the C basis. So the top entry is 14/16, and the second entry is minus 27/16. And what this is telling us is if we go 14 over 16 times the vector 5, 3, and then minus 27/16 times the vector 2 minus 2, and we take that linear combination, that is going to give us the vector 1, 6 back.